Okay, so what we're going to look at today is we are going to look at trig identities. So what we're going to do is we're going to start off with a right angle triangle, nice straightforward right angle triangle that you would have seen many of in GCSE. So all I'm going to do is I'm going to label up this triangle in terms of this angle here, which I've called theta. So using our GCSE knowledge, we can label this side as the opposite, this side as the adjacent, and this side as the hypotenuse. Okay, so what I can do now is I can write down a number of statements that I know to be true about this right angle triangle. So I know that sine theta is the opposite over hypotenuse. I know that cosine of theta is the adjacent over the hypotenuse, and then I know that tan theta is the opposite over the adjacent. I also know from Pythagoras' theorem that O squared plus A squared equals H squared. So all I've done is I've basically started off with a right angle triangle and then just written down a few basic facts that I'd expect a GCSE student to be able to do. Now what we can do with this information now though is derive some trig identities, okay? I'll talk about what I mean by an identity shortly. So the first one we're going to derive is we're going to say, well, what happens if we take sine theta, divide it by cosine of theta? Okay, so using the definitions I've got here, sine theta is O over H, so I've got O over H here, and then I can divide that by cosine of theta, which is A over H. Now there's a few different ways we can think about simplifying that. I would think about basically multiplying the numerator and denominator of the big fraction, the whole fraction if you like, by h. So if I multiply this numerator by h, it would cancel with this h down here, so we just get O. And then if I multiply this denominator by h, I would get A down here. Okay, so what I've shown is when I do sine theta divided by cosine of theta, I end up with the opposite over the adjacent, which is tan theta. Okay, now what we've shown there is a trig identity, and we can write it as such. Sine theta over cosine theta is the same as, so I'm using this equivalency symbol here rather than an equal sign, to tan theta. Now this is an identity. It's an identity because this is true for any value of theta. If we had an equation, for example, like 2x plus 1 equals 3x minus 9, for example, that's true for one value of x. This here is not an equation, it's an identity because it's true for any value of theta. So this is a really important result, so important I'm going to put it in a box, and that is our first trig identity. Okay, for our next one, we're going to do something else with sine theta and cosine theta. Just before we do that, just a quick aside about notation. If we want to take cosine of x and then square it, we could write it like that, but usually it's denoted as cosine squared x. Okay, so when I've got this written down, I'm talking about cosine of x being squared. If we saw this written down, this would usually mean cosine of x squared. So this and this are two very different things, and we just need to be aware of that for the next part. Okay. So next thing we're going to do is we're going to take sine of x squared, which you can write as sine squared x using what I've just talked about, plus cosine of x squared, which again, using this notation, we write as cos squared x. And I'm going to see what happens here. So again, using these definitions from the top, I can say, well, sine of x squared would be O over H squared. And then I can add on to that cosine of x squared, which would be A over H squared. And now I can have a play around with this and see what happens. So squaring each of those fractions is going to give me O squared over H squared plus A squared over H squared. We've got a lovely common denominator there, so of course we'll combine that into a single fraction to get O squared plus A squared over H squared. If we go up here, we can see that o squared plus a squared is h squared. So I can use that to replace this o squared plus a squared with a h squared. So we get h squared over h squared, and anything divided by itself is 1. So we've just proven our second trig identity, which is that, I've just realised I've used x there rather than theta, which is that if we have sine squared theta plus cos squared theta, or sine squared x plus cos squared x, or sine squared y plus cos squared y, or whatever we want to use, it will always be equal to 1. It's an identity, it's true for any value of theta or x or whatever variable we're using. So that's our second identity. So our second identity is sine squared x or theta plus cos squared x is the same as 1. Okay, and again, this is a really key result, something we're going to use time and time again. It's also commonly used in slightly rearranged form, so it's not difficult to see that we could rearrange that to give us that cos squared x is the same as 1 minus sine squared x, and sine squared x is the same as 1 minus cos squared x. And those results are so important, I'm going to put them in a box. Okay, so you've got two key trig identities that you need to be familiar with and able to use. Okay, so how do we use them? Well, we can use them for solving some trig equations, and that is what we'll get onto eventually. But what we can use them for is for proving some more complex trig identities. Okay, so I'm being asked to prove this trigonometric identity. Notice how it's not an equation, so we can't start doing the same thing to both sides and try and find out what x is. We need to show that this works for any value of x. So I can't take both sides and start manipulating from there, because that would be me assuming that these two things are equal to each other when I need to show that they are identical to two different things. Okay, so what I need to do is I need to start off with one side, either the left hand side or the right hand side. I would recommend starting off with the side that looks like is most difficult, most to do with kind of thing. So I'm going to take the left hand side. So I'm going to start off by saying the left hand side, so LHS, left hand side, equals cos of x over sine x plus tan x. Okay, so all I've done is written down the left hand side. And what I'm going to do now is I'm going to play around with this trigonometric expression and see if I can manipulate it and turn it into the right hand side. Notice how I've got my key identities written over here, and I would always recommend you have them written down so that you are able to kind of refer to them and use them as you need. Now, if we have a sneaky peek at what we're looking for over here, it involves sine and cosine. There's no tan there, is there? So if we can get rid of this tan of x, I'm going to do so straight away. So I'm going to leave that first cos of x and sine of x as they are, and then tan of x can be replaced with sine x plus cos x. Okay, so I've now got rid of tan. I've got something that only involves cos x and sine x, and I just need to muck around with this and see what happens. So what I'm going to do is I'm going to combine them into a single fraction by giving them a common denominator of sine x cos x. So to give this first fraction a denominator of sine x cos x, I need to multiply the numerator and denominator by cosine. So I'm going to end up with cosine x times cosine x, which is going to be cosine x squared, over sine x cos x. And then for the second fraction, to get my common denominator of sine x cos x, I'm going to have to multiply, then I've done it wrong. No, I haven't. Okay, so to get my denominator here of sine x cos x, what I'm going to need to do is I'm going to have to multiply the numerator and denominator here by sine x. Okay, so now I've got a common denominator. I can combine those two fractions and get cos squared x plus sine squared x all over our common denominator, which is sine x cos x. Now this numerator here, cos squared x plus sine squared x, should be looking familiar. We know no matter what the value of x is, it's equal to 1. So I can now replace that numerator with 1 and get 1 over sine x cos x. And we've done. We've shown that we can take this expression here, manipulate it using our identities into this side. So we're done and dusted. Okay, we've proved the identity. We've shown that this is always equivalent to this. Okay, so let's have a go at the next one. So for the next one, we've got a couple of reasonably formidable looking fractions there. I'm going to start off again with the left hand side purely because I think there's more to do with that really. So what I'm going to do is I'm going to just write down that left hand side. And then I'm going to see what I can do. Now here, if we have a look at our identities, there's nothing I can do any direct replacements with here. These are cosine of x's, not cos squared x's, so I can't use any of this. So what I'm going to do is I'm going to put them into a single fraction. So as before, I'm going to do that by giving them a common denominator. This time our common denominator will be 1 plus cos x, 1 minus cos x. So I'm going to have to multiply numerator and denominator here by 1 minus cos x. So the first fraction will become this. And then my second fraction, well, I need to multiply numerator and denominator by 1 plus cos x. So I'll get 1 plus cos x over our common denominator, 1 minus cos x, 1 plus cos x. Okay. So now when we combine these into a single fraction, we're going to have 1 minus cos x plus 1 plus cos x all over 1 plus cos x, 1 minus cos x. Now if we have a look at what's in our numerator here, we can see we've got a negative cos x and a positive cos x that when we collect together are just going to cancel each other out. So my numerator is just going to become 2. And at this point I'm going to multiply these two brackets together. Now because it's a difference of two squares, when I multiply these two brackets together I'm going to get 1 minus cos squared x. Okay, and then if we refer up to our trig identities, we can see that 1 minus cos squared x is the same as sine squared x. Okay, which is the right hand side of our identity. So we've shown that we can manipulate this to turn it into this. We have proved the trig identity. Okay, so let's just have a look at a couple more. So another one here. Now having a look at this one, again I'm going to start off with the left hand side. It happens to be every time, I think for all these examples we're going to start with the left hand side. It doesn't always have to be that, okay? Just start off with the side that looks like it's got the most to do with, okay? So I'm going to start off with this side and basically I'm going to square everything. I'm going to multiply everything out and see what happens. So here I'm going to square out this one here. Now of course none of you will think that to multiply this out we just square the 1 and square the cos squared x. We need to treat it as a pair of double brackets. So when I multiply this out I'm going to get 1 minus 2 cos x plus cos of x squared, and then multiplying out this one I'm going to get 1 plus 2 cos x plus cos squared x, and that's our left hand side, isn't it? Okay, so all I've done is I've taken the left hand side, multiplied everything out. So now I'm just going to tidy up, see what happens. So tidying this up, I've got a negative 2 cos x and a positive 2 cos x. They're going to cancel each other out. I've got 1 and 1, 1 and 1 is 2, and we've got 2 lots of cos x squared. Okay, so now we've got this. it's not anything like this, is it really? So what can we do to make it more like this? Well, I've got a cosine squared x and we're aiming for a sine squared x. So I'm going to use this identity here to replace my cosine squared x with a 1 minus sine squared x. So I'm going to have 2 plus 2 lots of 1 minus sine squared x. And then I'm going to multiply out, tidy up. So I'm going to have 2 plus 2 minus 2 sine squared x, and again hard sums, 2 plus 2 is 4, and I've got me minus 2 sine squared x, which is our right hand side if I'm not mistaken. So we're done. Okay, so one last example. So this time got more going on. We've got tan in here again. We haven't got any squareds, so for the moment it doesn't look like we're going to use any of these, but we'll see what happens. And once again, I'm going to start off with the left hand side purely because it looks like there's more trig I can do with that side basically. So I'm going to take this, and again, looking at what I'm aiming for here, there isn't a tan there. There also isn't a sine there, but there isn't a tan there, which I can easily replace with sine over cos. So that's what I'm going to do to start off with. So I'm going to have cos of x plus sine x over cos x multiplied by this sine x. Okay. And then what I'm going to do is just tidy up this term here. So I'm going to end up with cos of x plus, I'm going to multiply this fraction by sine. I'm going to get sine squared x over cos x. Okay. So at this point, we don't appear to be much closer to what we're aiming to get to. But these trig identities is a bit of a difficult skill, and it's just something you need to keep on persevering with. Do some more maths, see what happens. Sometimes an approach you take may not get you to where you want to be. In that case, you just have a little cry and then start again. But in this case, there's still some maths we can do here. So what I'm going to do is I'm aiming for something that only contains cosines. So I'm going to replace this sine squared x. Let's do that, see what happens. So I'm going to replace sine squared x with 1 minus cos squared x. And of course, what no one is going to do at this point is start cancelling these down, because we haven't got cosine as a factor of the whole of that numerator, so we can't cancel anything down here, so don't even think about doing that. Okay, so what we're going to do is we're going to try and combine this into a single term. So the way to do that is to turn this into a fraction with a denominator of cosine. At the minute, we could write that as just cosine over 1. So I'm going to multiply the numerator and denominator of this by cosine, because then I'll get a cosine in the denominator. We'll have common denominators and we can add them. So I'm going to write this first fraction by multiplying numerator and denominator by cosine of x as cosine of x squared over cosine. And then I've still got my second fraction over here. So let's combine them into a single fraction now, see what happens. I'm going to have cosine squared of x plus 1 minus cosine squared x all over cosine of x. And then what happens is we've got a positive cosine x, negative cosine squared x, pardon me, and negative cosine squared x. They're going to cancel each other out. So I'm just left with 1 over cos x, which is the right hand side. So at that point, you would be perfectly entitled to do a victory lap of whatever room you're working on trig identities in. So that's it. A brief overview of the 2 key trig identities you need to know, how we can apply those to prove more difficult trig identities, how to structure that properly, start off with one side, manipulate it and show how you get to the other side. Attached to the task you got the link to this video from, there is a sheet that has some hints and tips, a further example, and some questions for you to have a go at yourself. So have a go at those yourself. As I said, sometimes you might feel like you're going down a bit of a dead end, But the key is to keep on going, and if it really doesn't work, have another go, try something else, maybe even start with the other side to the one you started off with the first time you attempted the question, and see how far you get. If there's any you're really struggling with, then of course take a picture of what you've done and send it through to me, and we'll have a look, and I'll try and help you best I can through the VLE. Okay, thank you.